welcome to the analysis of algorithms evaluating quality for Comp 2503. Now this is the one part of the course where we kind of take a step back, and we're not really dealing again with physical programming, syntax, semantics. We're more worrying about, okay, well, given an algorithm, how can we start having terminology to talk about its quality? And specifically for now talking about its time complexity, so how long does it take to run when we start increasing the amount of data that has to go through the actual program itself. Now, as always, I like to include a video to start this, at least hearing it from someone else about how they talk about these terms. So with that, you got your first kind of quick introduction to the idea of analysis of algorithms. I always find this difficult to win people over for what the point of this is, because a lot of us are getting too used to just a faster computer. Who cares how long it takes? You don't even know there's a difference, even though your program could be excessively inefficient in what it's doing. But there are cases when you're coding where this does add up and starts causing problems later on. So right now for us, like, analysis of algorithms can be its own whole course and field itself that, just like data structures, branches off further past this course. So I'm only here to give you the first flavor and introduction to kind of what to expect. And really, it's also to give us another language or terminology to be able to talk about different algorithms and be able to compare them, especially when those algorithms are designed to solve the same problem and you're making decisions of which one to use, or we're dealing with different operations that are happening against a data structure and we want to know which one's better. Or even if we go beyond just the basic ADT of a data structure and think about specific different implementations of a specific one, like different stacks that are implemented that have all the same ADT, but they're implemented in a different way, and that could impact the overall execution time of your program. So the analysis of algorithms, it's like the same problem can frequently be solved with different algorithms which differ in efficiency, so how long they take to run. We need a way to compare the algorithms and pick the best one for the situation at hand. The efficiency of execution of an algorithm depends upon the hardware, programming language used, compiler, programming skills, etc., and everything from there. But we still need some kind of common language to be able to talk about, well, how is this done? So to evaluate an algorithm's efficiency, logical time units that express a relationship between the size of an input and the amount of time and space or memory that's required to process this input is needed. So this just more means as we give it more input, say if this was a really huge file with a couple million entries in it, and we have another file with like 1 trillion entries and 2 trillion and like everything else beyond that, like how long would it take your program or this algorithm to actually execute this? If we were caring about memory on the actual device, how much memory is it going to actually take up over time as it runs? If we're worried about efficiency or finishing, how long will this physically take, and how does that impact the rest of the actual program or whoever is using itself, and that frequency of data coming in there. So our goal here really is the efficient use of resources. That's what we would hope with programming. Unfortunately, a lot of times some people just get her done, just whatever's the quickest to solve this problem, but that's not the best choice overall and what that can cost. Like any program, if you experience yourself, when it's really slow, probably your user base does not care to use it. The time overall, if it takes a long time to run the execution of something, how does that impact other processes within real world or business that this is being applied to? Especially if we think nowadays with games, how fast people react to latencies of anything that happens with a game, for graphics to lags to commands and overall performance, and that's like becomes a huge thing for people. Well, you need to worry about the efficiency of resources. And so right now we're thinking about these just about time. So how long does the algorithm take to execute on a given data set? And memory, how much memory does the algorithm use as it executes? So which algorithm is better for the problem we are working on? And how can we have a common language to talk about that? Now, other factors that you need to take into consideration at any time when working on programs is, one is generality of the algorithm. Like, does that matter? Do we want to be able to reuse the code, or if we don't care, it's just going to only be for this specialized task? How much programming effort this is going to take on an individual or group of people, and the cost it will take for that. The problem size, so do you know the population or what's kind of working with? Like, what will the data sets be like? How like heavily computational will it be? And things like growth rate functions. So as data sets grow larger, how long does the algorithm take to execute? Now, don't worry, growth rate function you may not have heard of, but it's something we're going to talk about this in this course in a way to convert talking about a program, how long it takes to execute, and having a mathematical formula to roughly estimate that so we can visualize and see how would things change over time. Now, in this course, we'll only be concentrating on time complexity, also known as asymptotic complexity. And so the definition for asymptotic complexity is as the input becomes larger, how long does it take to complete the execution of the algorithm? So for example, the time it takes to compute a class average when you have n students. If we have 5, it's fast. If it's 1,000, if it's 1,000,000, if it's 1,000,000,000, how does this change over time depending upon the algorithm you had? So again, asymptotic complexity, as the input size becomes larger, how long will it take to complete the execution of the algorithm? And this is generally graphed over time. Well, you'll show different inputs. You say for n of 100, 1,000, 1,000,000, whatever, and you're kind of graphing it out as that increases, what time will it take and what will that look like over time? Here's another quick example of 3 algorithms for what is basically a simple problem. So for any integer n that's greater than 0, we want to be able to sum all digits from 1 up to n. That's just say the problem. And there's different ways of going about doing this. So 1 is the most horrible, so algorithm B is the most horrible brute force way. It works and it solves it is literally just count. So for every digit from 1 up to n, go through each one, just sum up like 1, 2, 3, 4, then 1, 2, 3, 4, 1, 2, 3, 4, 5, and so forth, and just add up each individual single counting. Algorithm A here then takes a little different of just, well, hey, how about we just sum up each number and get the computer to do it? So count up from n. Or algorithm C is going back to a mathematical formula that given this series, you can use this formula to get the sum of all those digits beforehand. And we need to compare and contrast these. They all solve the same problem, but we'd have to think about, well, over time, how long would these take to run? And you think, well, if we get to larger n's, this loop here, n, will take more iterations, so there'll be a slight overhead. This one here, as we get to n, there'll be even more, so you have this n plus this loop that's running every time, so it's doubling everything up, versus this algorithm C, which is just one straight line as we do it. It's going to be some basic calculations that there's no extra steps as n increases. So we get one that's almost constant, one that seems to grow linearly, and one that's kind of going to grow exponentially. And we'll talk about these more, but they're just quick small examples to show how you can have 3 different algorithms to solve the same problems. And one that's easier to code and smaller, but maybe harder to understand if you don't have the mathematical background or don't know to go look for that formula. One that we're used to for coding, and one that's just fully brute force. But they all can take different time as n increases. This is constant, this will be linear, this will be like exponential, more like squared values. So another question that comes to mind is like, how can we time an algorithm? And so first one is physically time it. Like every computer has a clock. We can request what the current time is in milliseconds it's been running, and we can take things like take the time before the algorithm runs and the time after it finishes, then subtract these 2 values and get the runtime. And do this for multiple sizes of data, and then see how does that change over time. So increase the size and time it every time, and then see what does that graph out to. But a problem with this is that this can be affected by other things running a computer at the same time. That all of our modern day computers are multitasking, and it can only run X number of programs depending upon the number of threads or cores that you have in the actual machine itself. So it can be affected by this actual growth. So your program may be running, but the operating system itself is switching out tasks and maybe putting your program to sleep for a bit while switching in another one. And you don't notice that as a human because it's so fast, but internally for a computer, that can slow and change things. So to deal with this, we would need to take multiple samples to average out different cases of it to get a little bit more accurate, so more time. And to do this, we would also need to implement the actual algorithm. And this is time and money that's required. So if we're dealing with trying to decide beforehand and more of generic as we're designing, which some people in analysis algorithms do, is more on the mathematical side before you go deeper and not physically implementing this for time. And that's on the other case. We're not going to go further into that in the timing. It's just showing that if we want to time an algorithm to get this, we have to do specific things, and there's other factors that come into play. Now, an alternate way of doing this is to use an estimate of it. And this is more the mathematical side. We're not going to go super deep. We're in this course getting a basic kind of overview of it, but we want to determine an estimate on the runtime based upon the number of operations that we execute. And so this is an estimate that if we just going to consume like a basic operation of adding, maybe that's a constant time of 1, we'll call it that, and every time it's repeated, we get an estimate that's close, may not be the exact timing it takes to run, but if in the beginning, right, for us, we're doing estimates of timing, this is good. Maybe you need other timing algorithms, and you need to refine things with physical coding, that's a whole different thing, but for us on the theoretical side that we're dealing with for this course, we can start getting estimates. And so to give a term to that is, in other words, this means build a growth function. So this is a mathematical representation of the execution time of an algorithm that represents its asymptotic complexity. So as we give it a number n seeing the size of the actual input, or n representing the level of complexity, it'll give us back the rough execution estimation time of what it takes and give us a visual way to look at the actual algorithm. And so we will be going through in this lecture a little bit about how to look at growth functions and how to develop yourself, and then get to that big O and kind of generalized family of algorithms in a way to talk about the actual execution itself. So a growth function shows the relationship between the size of the problem n and the time it takes to solve the problem. And so an example below, you'll see something, your functions of like t of n being the input equals 15n squared plus 45n. And so this is representing the execution time and the operations from the actual an algorithm. And so when you give it n, you have this function, and we can graph everything out from there. Now, if I go to code, we can kind of get a visualization of this in a different way. So if you see the code that is on the left, we can see a basic algorithm for finding the average. So given an array of numbers that you can see up here, it's just going to go through generally summing up all those numbers and dividing by how many there were and returning that back to us. So how many iterations will the loop take as you add more numbers to this list? And so right now, for us, the time complexity of the n, and as it grows bigger, is the more students we have or the more numbers we need to calculate an actual average. So as that goes up, well, how will the algorithm change itself? So example, if we look at list 1, list 2, and list 3, list 1 down here in the main has 3 numbers, list 2 has 7, and list 3 has 15 numbers. Now, when we go in here, well, how would this kind of run? So we're calling on each list, and we know, well, this is going to take, each of these 3 prints here is going to take different times to execute to get the actual average for making this call. And we need to look at the algorithm, see, well, what could be affecting stuff if we just kind of think of basic operations and time. So the first thing to think about is that no matter what the list size is, we will always have to set sum equals to 0. And we'll always have to do the sum divided by the numbers of length we have here returning this number. So that always has to happen. And so we can think of this as one operation, this is another operation, and for right now, to give it an estimate, we can just call this one time unit to give thread. So this is 1, and this is 1, and it'll always be constant. So we'll always have those 2 steps. So no matter how long this takes to run, we'll always have an additional 2 time units that will be tacked on to this algorithm. Now, if we go through and kind of visualize the physical steps the loop would be doing given the different arrays, the one with 3, the one with 7, and the one with like 15, for right here, is that, well, this is going to be the loop we have to go through, and it's going through starting at 0, going up by 1, and going up to the length of the list. So this overall loop here, say if we have 3 elements in the array, we'll take 3 iterations, then 7 iterations, and then 15 iterations each time. And then inside that loop, we just have one line here that's going to constant again, and it's going to be repeated this number of iterations, and then we're calling those overall time units. So we can think of things like, okay, if this is 3, we come in here and we know, okay, this is going to take 1, this is going to take 1, so we can add those together and get the 2 that we see over here. This loop is going to take 3 time units that we see here, and overall this will take 5 time units with an array size of 3. And going a little quicker, we can see if we go to list 2, which has 7 elements, again, we've got the 2 here, plus the 7 time units, we get 9. And same thing for the last one, we have 15 elements, 15 plus time unit, we get 17. And we can kind of generalize this to being, well, we always have the 2, and this first number here is really dependent upon n, or the size of what we're dealing with. And right here, we can generalize that to n plus 2. So the number of steps for the loop, plus 2. So we get the array size. And I'll be giving you some like rules in the future here for if you're given code, getting the time complexity, just for practice as far as we care for this course. But this is going to demonstrate that growth function now that, well, we have a general one here for n plus 2, and we know from generalizing from look at these that we get the values. But this will now give us a case of like how we can graph this out and see, well, if we were to use this in a case for a million, what could we roughly execution time, and is that good enough for us, or is there a better way of doing it, or just having a way to visualize what will actually happen? So here we got an example of graphing it out. So the growth function for the find average is t to the n equals n plus 2. And if we graph it out here where the bottom is the input size and the top is the number of steps it takes, we can kind of see we get a linear growth. It's just a line going from here. So linear growth going up. And so basically as we increase the input, there's basically an equivalent increase in time, and it's not going too crazy as we go up. So we know we're okay with this. We get a rough estimate for how long the algorithm would take, and depending how this will affect the rest of the program that use that algorithm again and again. Now, determining the growth function. So rules to follow. Now, normally, you'd be dealing with a whole lot more math. You wouldn't even be looking at code when you're dealing with this, if you're going for course for algorithm analysis. But for us here, for this degree, it's good enough to just get a feel for how growth functions work. And so I like to start where I give you a piece of code and you work your way back to show the growth function from it. Because we're all used to seeing code, we can understand and interpret that. And so then we know we can break that down and then kind of use our rules to get this growth function that we need for time, and then to be able to do work with it past that point. And so an estimate of how long it takes to run. And then especially if we have a couple algorithms that look exactly the same, that do the exact same job, so solve in the end, but may do it in a different way, and we want to compare which one's best based upon its asymptotic complexity, i.e. how much time does it take to execute as the inputs increase. We need the growth functions to be able to do that. We even need the growth function to talk about what's the big O of this operation. So what I'm going to provide here is some basic rules to follow that for any test or anything else or assignment that we have for this course that you can use. And we've got some examples. So the first rule, the consecutive program segments. So this is basically when you have an overall program, if you can break it up into chunks that it's one consecutive, so the one segment that has to run first, followed by the next segment, followed by the next segment of code, all you need to do is then you can break it up by those segments. You can figure out the individual growth functions for each of those segments, and then to bring it overall together for the entire program, you just add it together. So for whatever program you have, so t of 1 of n plus t of 2 of n plus t of 3. So each of these individual sections, you just add it together. And it kind of makes sense that the time complexity of one chunk of code just adds on how long it takes to run for every segment. So each segment afterwards, how long does the overall program take? And so that's how we can take, say, a bigger function or bigger chunk of code, first circle it and break it down into what we see as consecutive separate chunks that are looped together or chunked together, and then figure out the time complexity of each separately and then just add it together. And so the example here, you can see the chunks that, well, if they're individual statements, those can be all grouped together. If it's a loop, well, then the loop and everything inside of that loop that's going to iterate would be one chunk, because that all has to execute before you go past. And the same thing in if or in if-else ladders or switch statements or stuff like that. They can be all grouped into one segment as well. So basic, another rule is basic calculations or operations. Is that basic calculation operations such as the following only take one step. We can think of that for the time units and generalizing this. So the growth function is a constant of 1. So example, just a line like sum plus equals numbers 1, there's no ifs, there's no loops. That whole thing will just summarize as being a constant of 1 time. If we had the following code, we could apply the rule from above and the consecutive rule to get the following growth function. And so the idea is if we just have these 3 lines here and we're doing a consecutive one line after another, we can break into chunks being 1, 2, and 3 chunks. We know then that we can add all the time complexity for each chunk together to get the overall time complexity of this section here. So we're good. And so we look at this one. Okay, that's a basic initialization of an array with specific values at the start. So I'll just call that constant 1, another constant 1, another constant 1. So that's where we get the 1, 1, 1. And then bringing it all together, not to leave it all plus like this since we can do more of the math, that the time complexity of these 3 lines of t of n. So no matter, this is kind of saying constant time, being that no matter how n increases, these 3 lines will always take a constant 3 time units to execute. And don't worry, I've got examples coming up. I just want to go through the rules first, and we'll have practice in future tutorials as well. So first, for now, the next rule is for loops. What you have to do is you have to figure out the growth function of the loop code and times it by the number of iterations the loop will execute. So when we look at any loop right here, we have the loop overall. We want to make a segment out of every bit of code that is inside of the loop. Then we figure out first the time complexity of what's inside the loop, and then we figure out how many actual executions or iterations this loop will go, and we times the number of iterations by the actual growth function itself. And you'd expect that if this internal code for one iteration loop is going to take this long and we're doing m iterations, it's going to take m times what the time it takes to execute just one iteration. Now, to give you a quick formula in the beginning, especially since we're going to deal with basic loops and nothing that's too complex to figure out how long it takes to run, basic for loops where we can know the iteration, what you can work out for this is you just look for what is the end value minus the start value, and then you divide that by how many increments you're going up. So you're going up by 1 or going up by 2, and then you just take the absolute value from this, which means if it's negative, if this results to a negative number, just drop the negative and it's always just going to be positive. Now, conditionals. Next thing here is first you figure out the growth function of the conditional, so what's inside the actual code, so each if, each else if. Figure out the growth, so that's the conditional, that's the statement at top. Figure out the growth function for the if body and any other paths it could take. And then you look at all the paths it could take, so each if or body for if else, and find the largest growth function from the step 2 that you had and add that to the growth function for step 1. So pictorially more seeing this is that this is the conditional. So you look at the conditional in here and think, okay, well, how long will it take to execute this one statement? Most times this is going to be a constant of 1 because you're doing basic comparison, but where it could take longer is like, what if you had a function or method call within here and that method's going to take extra time to actually execute? So you want to take that into account. So we figure that out. Next, we have each segment, which is an each if or else if statements that's all grown together. Since this is an if and else if, it needs to be connected, or if there's an if and else or so forth or switches, you then kind of chunk out each segment, each if or each else if segment, figure out the time complexity between them, and then between all of them, pick which one grows the fastest. And we'll have a way to talk about growing the fastest when we look at other graph functions. So it's more, you would draw it out for an exponential algorithm or linear or constant or logarithmic function from there. Now, last rule for dealing with methods for function calls. Basically here is figure out the growth function for the method itself. So you do the internal code, you don't worry about the call here, but you just basically figure out what's the growth function for here. And then in the original program, anywhere you see the actual call to that method, you replace it with the time complexity it took for just that one execution of that method. Boom. So quick rule, quick summary of all the rules. But now we need to go through and actually go through some examples and play with this. So first, we're going to deal with that original first find average one that we know it was n plus 2, we're rough estimate, but here's following the actual rules for doing this. We want to look at the entire program, and the first step I always say when starting this, because we're doing for, like, in this case not a program, we're just doing for one method, first step I would do is try to break it up into chunks and what makes sense. If I was looking at this, I can see I've got the one continuous line here, this needs to execute. We have this entire loop that needs to execute, so that's another segment. And then we have the return statement, which needs to execute after these two ones that are above it. So that's why you can see right here, I've broken it into the 3 segments, and then I've just labeled it myself, being that this will be like time function 1, time function 2, time function 3, and then I know using the consecutive rule is I just once I figured out the time complexity for these 3 individual segments, I just add them together and I will have the overall time complexity that I need. And since all these 3 together make the entire method, then this t of the n will be again the growth function for that chunk of code. So said before, now using the actual basic calculation operation, that these are basic ones, the time complexity of this would be 1. So this is 1 and this is 1. You can see this reflected here by me saying, okay, t of n now is 1. That's the only line of code we have here. t3 equals 1 for this line of code. And then up here, I've replaced it. See, match with the blue is, okay, well, now that we know those constants, replace the t of n's with what the actual growth function is for those two segments. And now we've narrowed it down to, okay, our time is the t time function 2 plus 2. Next, from here, we need to use the loop rule to do this. So remember this, you figure out the time complexity of the internal body. You then figure out how many iterations that you have from here, which for us will be right here is the ending value minus the starting divided by how many increments you get and taking the absolute value of that, timesing it by the time complexity inside the loop, and then that gives us overall our T2. So here we can figure out we got T4 again, so breaking these into chunks, segments, we need to figure out the iteration, how many iterations. We then need to figure out and breaking down the time complexity of the internals. In this case it's easy, it's just one line, so this is going to be that basic rule again of a constant time of 1 here, and then we've got m that we need to figure out. So there we go, time of 1, change it within here, so now t times 2 is equal to m times by 1. And then for here, we just need to figure out, okay, how many iterations? So n value minus start value divided by increment, absolute value. Here, this is numbers.length, so the length of the array, minus 0, which is our starting value, divided by 1, since we're incrementing by 1. And in the end, we just get numbers.length, because that's 0 divided by 1, we get this. And to generalize this, since this is more of an array, we know it's going to change, and that our complexity is dependent upon the size of the array. So we will just make that generic and making that our input, saying that it's n. So values relate to the work that we actually call it. So bringing that all back here, this means that our time function here is then just n, so n iterations times by a constant 1, so overall n, and we can change this up here at the top and we get n plus 2. So we're getting the same thing we did before by rough estimating, but this is now using all those rules and bringing everything together. Now here I have a class activity, so for the people who are doing this, watching the video at home, I suggest you stop now and try to do both of these on paper using the previous rules. I'm going to go through it on paper here in a second, and you've got the solution on the actual next slide. So I'll give you a second to pause. And then for those listening or coming back, welcome. We will switch and try to do these now following the similar rules, but doing it ourselves on paper. So I will switch to something that allows me to actually draw and write on my screen. And we will start with the first one that we have here. Now we have overall just a loop, nothing big here. I can break it into, again, this first chunk here that's my iterations, and then this next chunk here, which is the internal body of the code. I know that for this internal body of the code, it's one line, so okay, that makes it easy. That's that basic calculation rule. This will have a time complexity of just 1 for this one line. And next we need to figure out the actual, how many iterations will we get from this. And so we know that's the end value, which is this n minus 2. So you get n minus 2. We subtract from it the starting value, which is subtracting 0. And then we want to divide by how we're going up here. So we're dividing this whole thing by 3 right there. We can then shorten this by, well, that subtraction of 0 does nothing, so this is just n minus 2 over 3 right here. And then I can make this even smaller by, well, if we're dividing by this, we can use another rule, which is we can just split up the division. And that's 2/3. So we're just taking what we have here in the bottom and we can subtract it across. And then to make it a little bit easier to read, I can just take out what we have here. So the 1/3 that's here and timesing it by n minus 2/3. So this in the end is how many iterations the loop will actually take. And we want to times that by, boom, that inner constant there. So I'm just going to erase some of these since it's getting messy. So we know is we're just timing it by 1, so in the end our growth function for this, so t of n equals 1/3 n minus 2/3. So weird fun with fractions. Now our next one is that we have double loops for this, but we can still follow the same rules for segmenting stuff up, is that we have one segment here for the first loop, and then we have another segment internally, which is the second loop. So we need to figure out again, like how many iterations does this first one take? So this one right here. Then we need to figure out how long does this take to actually run. And we can see, keep breaking these down. So I'm going to figure out the internal side here first and then keep going. So we have another loop. So look at this. Okay, well that's one segment. And then we have this inside of that loop. So we need to figure out the number of iterations this loop does, and then we times it by how long this takes to run. So I'll remove this to make everything a little bit easier to read. So starting down here, right there we can see again basic operations there, so that'll take time 1. We then have our loop here. We need to figure out the number of iterations, and we use that rule again of the end subtract by the actual starting. So the end subtract start, and then divide by the number of iterations and take the absolute value. So here we get n minus 2 subtracting 0 all over top of 1, which simplifies quicker down to n minus 2 over 1. Because subtracting 0 doesn't do anything else, and if we divide these by 1, we just get n minus 2. So we know that this inner loop will take n minus 2 iterations to actually execute. And then bringing this all together, we have to times n minus 2 times by 1, which is very easy because it's just by 1. So the overall time complexity of the inner loop will take n minus 2 steps, depending upon the input. Now we have the internal of this, of how long this internal loop is going to take. We now need to figure out the iterations for this outer loop, and we times it by this overall value. So starting from here again, the end minus the start divided by your actual iterations, or how you're counting up. So this is n minus 0 over 3, which then equals n over 3, and we can even write that as 1/3 n. So we get 1/3 n up here. So now we need to times these two things together to get the overall time complexity. So that's 1/3 n times by n minus 2. And the idea of doing this is you're just taking this and timesing it in here, and then you have the subtract, and then you're taking this and timesing it by the actual 2. So we get 1/3 n squared, and then minus 2/3 n. So again, we're getting this right here is n times by 1/3 n, because n times by n gives you n squared, and then the 1/3 here. We keep the minus, and then we just have the 2. And so that's 2 times by 1/3 n, so that's where I'm getting the 2 divided by 3 over n. So our end result of all of this is 1/3 n squared minus 2/3 n. And that's how long this will take, so as n increases. And then we can see our first examples now of, like, this first one right here is more linear. We have the n, and we have another case with the double loops, which is going to be more exponential as it grows up. So kind of you can think of one will kind of look like this as n increases, another one will look like this as the exponential kind of graph, if you remember back to your high school math. Okay, yes, let's go back to the slides and see how we're doing there. Compare to our answers, and Yep, this looks like right to me for what we got before. Okay. Now, continuing on from here, we have the next thing of another class activity. Let's go to doing the actual if statements itself. So I'll switch back to our worksheet. And what we have to work on now is this if statement here and trying to break it down. Now be aware, when I wrote up my formula before versus what's the solution, this looks different here. This t of n of 1/3 n minus 2/3 n's. That's just because I separated. Like this is still the same as being that n minus 2 divided by 3. It's just that this one up here, I split it further out. So the n minus 2 divided by 3 is the same as what you're seeing here. Now for if statements, when we're doing this, we want to again break things down to consecutive code. For this is the if and else are connected together, so they're not separate segments, it's all one loop. So this is all one whole right here. And you want to figure out the time complexity by first figuring out how long will this take to execute. You then figure out how long this will take to execute, and then how long this one here will take to actually execute. Once we have these, we compare these chunks here and see which one is max that you're dealing with, and then we add it to the time complexity of what you see that's up here. So this example will go faster because these two loops you're seeing here are the same loops we saw before. So all we need to figure out first is, okay, well, what's the time complexity of this statement? Well, in that if an n greater than 10, that is a basic constant time of being 1. There's no method calls or anything else. So that is 1. We then have the first loop, which we figured out was the n minus 2 over 3. And then we had this next loop right here, which we figured up here, which was 1/3 n squared minus 2/3 n. Right there. And now we want to see, okay, well, which one of these two is bigger? And it's kind of, this one was easier to see from this. Is more like you'd want to plug in a few numbers and see which ones grow faster. But we know right here we have n squared. And if you remember exponential will generally, like at lower ends, like say if this is 0, okay, well that's 0, you know, this is 0, it's my 2/3, kind of small. If this is 1, it's not going to grow. But once we start getting to 2, well, this is going to be 2, this is going to be 4. Once we get to 3, this is 3, and then this is 9. Well, this squared exponential will grow faster. And it's kind of, you can see by this rough estimate here of this is n squared. And so this one will take this second one will take the longest to run. So this is the time that we want to use overall. And so the point here is, okay, well, if that one's going to be, this else is going to be the worst case it's probably going to take to run, and this is its time complexity, we then just add it to what we see up here. So what we had for the conditional. So here we had 1, and we just go plus 1/3 n squared minus 2/3 n. And there we go, we've got our growth function for this if complexity. And this is just the worst case. So even though this is in here as being that this could run faster, the idea is, well, if the else is going to run, that's the worst case that we could have for the actual algorithm. Okay, let's switch back to the slides and we can take a look at the solution. And you can see, same thing. This time even written out the same as what we see before, breaking down the program and bringing everything together. So again, saying the constant time here, we had this one which takes this long to run, we have this one that takes this long to run, this else takes longer to run than what happens inside this if, so we use this as the actual max. So it's this plus this, and then that's where we end up right here with this plus the 1. Okay. So weird. It's not a super skill that you need beyond what we're going to do for the activity. It's just to get you a feel of relating between code and time and kind of making connection between when you see this mathematical function, you have to remember it visualizes code behind the actual scenes. So you'll get a little bit of practice on this, maybe something in the midterm, not huge. Now, a bigger thing that'll be useful for any job or anything else in the future is just kind of keeping your back pocket if it ever comes up, is dealing with what does the term big O mean and how do we deal with that? And this is more around the idea of grouping families of algorithms together to actually talk about them. So even though there may be a lot of different algorithms for solving different problems, there are certain ones that, well, no matter what the input size is, they only ever take this long to run, and others they take this, and they're completely separate sets from each other. So different classifications. So some are always really horrible, some are always faster, and so forth from there. So big O. So normally we don't need the exact growth function. What we need is the asymptotic complexity of that function. So here, asymptotic just means like analysis as it gets larger and larger. Gives us an upper bound on how much time or space grows as n increases, and referred to as the order of the algorithm. So the exact growth function gives you a feel for it and gives in timing if you're caring from that. And then when we talk about comparing some algorithms, we start going to the big O, which is just the worst case it could take. It could run faster in some inputs, but for some other inputs it could take way longer to actually run. And that's the order of the growth function. So big O, commonly written as a big O, is an asymptotic notation for the worst case, or ceiling of growth of a given function. It provides us with an asymptotic upper bound for the growth rate of the runtime of an algorithm. If you were to go further with this for algorithm analysis, there are others where you go lower bound and kind of sandwiching in between, but for this course we only care about the worst case instead of like the best cases of what happens, because we really want to minimize what's the worst running time that could possibly happen for an algorithm. So another good thing to get used to is kind of referring back to this chart. You'll see another version, other slides, is comparing stuff. If we thought of each one of these lines of being the n being the input over time and how long it took to take, and then you can see these different classifications of these algorithms as we execute these. That you have the line that's going up here that will log n. You can see in the beginning they may be close, but down to here, this log n is always going to be faster than n and way faster than n squared, and that kind of time that they'll never reach these inputs. They take longer and longer to run. And you can see where we start getting these different classifications for algorithms where they're not even close or overlapping with each other. They may overlap at smaller inputs down here, but for larger inputs later on, they don't at all. And then we can start classifying that, even though we may have some constant other stuff, we can say, well, the grouping of these is all right here, and they never cross over with these, and we have that family of algorithms. And talking about the big O and just that upper bound case and upper bound notation. So finding the big O based upon the growth function is not that hard. It just takes understanding what is a term, and then determining how you compare dominant terms based upon the execution time, which is, there's a rough chart for this you can always refer back to for the slides. So to find the big O based upon a given growth function for an algorithm, you look at the dominant term in the growth function and ignore any constants and any other terms from there. Kind of the effect that it's already basically the thing that's going to be affecting the algorithm's execution the worst. So basically, which term grows the largest quicker as the input size grows larger? Here's a chart you can refer to back in the future for tasks or tests or anything else for comparing which one's larger, and knowing that basically here you can see this big O, and these are the terms, so things that you'll see it times it against as far as you care for this course, and you're going from green here being the better up to red being the worst, or you see on this other chart of these are the fastest, these take the longest to run. And so when you're ranking for being the dominant, it's which one's taking the longest to run. So these ones here at the top are more dominant versus these are less dominant. And right here, so this is kind of giving you an ordering that, well, 2 to the n, or n to the squared, 3 here, x to the 3, these run way higher and more dominant than anything that you see down here. So terms themselves, when you're looking at the growth function, terms are these values you're seeing. So generally separated by your plus signs you put together for the consecutive segments is, well, that's one term together with another term that you have here. And so the dominant term in this one here you're seeing here is 15n squared, and you're dropping any constants just to get n squared. So how I got that, by looking at the chart, you can see we have n squared and n. We go back to the chart here and we can see, okay, here's n squared, n squared is above here in this chart, so this is the more dominant. Same thing here, you can see this is n, and here you see is n squared, so this is the one that's going to take longer to run, and being that it's more dominant. And so when we look at all of these, then okay, well we take the growth function, the house dominant term, and drop any constants. And so this is the term that's growing the most, and we drop all other terms, which is 45n, and any other constants that we see after that. And this is another constant that's in front of it, so we don't even care about the 15, because 10, 15, 20 squared doesn't change anything from here by much. And so we just drop all that, and we get the n squared. So again, just to repeat that, you look for the dominant term, drop all other terms, and then drop the constant that you see in front of the actual term if it's times by anything else. And you should just end something with n to some kind of power or whatever else from the terms that you were seeing here before. Another example of this is if you were literally just to start plugging in some values, you can see which one's affecting this overall the most. So here you can see, say, the number of things we're dealing with, say the number of dishes we had to deal with or something else. And so this is your n as it increases, and these are each individual terms. So you have your 15n squared here, this is your 45n, and these are the values, and this is the result coming together. And you can see in the beginning, well, the 45n is kind of higher, but that quickly changes. We get to input of 2, we get to 5, and we even get up here to 1,000 or up to 10,000 or 10 million. And you can see, oh, hey, look, this number is way larger and has more of an impact on the overall number. So this term here is more of the overall dominant term. Again, and we can just drop that constant and get n squared, and that's the most dominant term of the order of this function. And you can see that here again from our chart. So using big O notation. So once we've figured out, oh, we have to use big O notation to indicate that it's not a growth function we're talking about anymore. We're talking about the big O of that function, so the upper bound of how long it takes to run. So again, you look through the terms, you find which one's dominant, drop all other terms, so this one disappears, drop the constant, and it's n squared. So the order of this function is n squared, and we write out the big O as we do an O bracket, that value we got, which was n squared bracket for the above growth function. So I'm going to be expecting all of you, when you write this out, you don't just go n squared, you go big O of n squared. Otherwise, you will lose partial marks for this, because this is an indication that you're mathematically talking about the order of big O of the growth function that you see here. And what this does is it classifies it into a family that basically whatever algorithm this is, it's generally the same execution-ish time as n squared ones, but it will never go faster than an n algorithm, so an order n, and they're completely separate families from each other. So for us, for a class activity now, and again, if you're doing this, watching the video, I suggest you pause, do number 1, 2, 3, and 4, and get the big O, or the order of each of those growth functions. And you can use this chart to reference here, and then come back to this video. For us, getting the growth function becomes really fast for a lot of these, and we'll go through each one here individually. And you want to compare. We first look at all the terms. So we have this term here, second term, and a third term. And then we want to see, okay, I'm seeing an n squared log n, I'm seeing an n log n, and an n squared. And we know that up here are more dominant, down here are lower. So if we start here first, we have n squared. Okay, that's right here. This seems to be good. So far I look at that, that would be my first dominant term. If I go with n log n, we see here, okay, I've got n log n, but this is below n squared. And so n squared is more dominant, so this is still our dominant term. But lastly, we come here to n squared log n, and you can see, like, well, I don't have anything here that's of this complexity, but it does contain an n squared. So first off, before looking at the n log n, it is already n squared right here, so it's on par with this one. But then it's times by another value right here, and so even though this is n squared and this is n squared, I'm just ignoring the constants because they don't matter here of n squared, but this is going to grow larger as we go, and it's going to impact that this overall thing would grow larger than we had here. So even though I don't see it in the chart, I know, okay, n squared, those are the same as far as n squared, but then this one is times by another factor that will keep growing larger, and so this would affect and grow larger overall. So we drop these terms, and we know so far the most dominant term is this 45n squared log n. And so then we know the next step is, once we found the dominant term, drop any constants, which is this 45. And so we know that n log n right here is n squared log n is the order. And so this will be big O, so O bracket n squared log n. Number 2, we go through the same process. 23 we can throw away as a term. We look here at n. Okay, n is down here. We then have log n. Okay, well log n is below. We have here as well. But now we can see, okay, well I have one here that's not on the chart of n log n. Oh wait, it is here. It's n log n. So we have n log n. So log n up here, this is more dominant, so this is the dominant term. There's no constant, so we're okay. So we just go big O, so O bracket n log n. Okay, quicker through this one. You got 3 terms, dominant n, so you get n here. We have n squared that's here, but we have n to the 3rd that's right here. And this is going larger. If we had n to the 4th would be larger, so as this number increases it goes up. But anything in number 2 and n will be higher than anything from here. So we know that 7n is the most dominant. Drop the 7, we just get n to the 3rd, so that's O bracket n to the 3rd. And lastly, for this one that may be longer from right here, n squared n, okay, out of these two, this is more dominant. We have n, well that's like n squared is more dominant, everything from here, so this is still our most dominant. Then here we have 2 to the n right here, which is just some number raised to the power of n, doesn't matter if there's 6 or 7. This right here will always be larger than this for the actual overall growth. So this is our dominant term, and so for this growth function, we don't have to drop any constants here because this is 2 to the n. It's not a constant, it's a power here. We can't drop the 2 because it's being raised to the n. So this is O bracket 2 to the n bracket. Okay, so you can see that here. Dominant terms for each one identified, and then the right order. So again, don't just write out n squared log n. You put big O bracket that value. Now, lastly, we're coming to things like comparing actual algorithms. So, full whirlwind, and this is what we want. In the future, we're going to be basically, you compare the big O of it. And that's what we'll do for most of them when you're talking in generality for algorithms. But if I gave you 3 algorithms, I could require you to give the growth functions for each and then compare them to see which one would be the best, saying that these were all the same algorithm. The algorithm solved the same problem, but each one could take different time complexity to run. So step 1 is look at the big O of each growth function that you're given. So either get the growth function of the code, then get the big O and compare, and then you can look back to that original chart that we had here and say, okay, well, which one's more dominant? We always want the ones that are going to take the less time to run, so you would pick the algorithm that has the big O that's lower. If there's any cases when you're comparing where the big O is the same, well, then you need to go to step 2, is just compare directly the growth functions. So try plugging in the same values of n that are increasing going up from larger and smaller values, so some kind of sample, and then see which one looks better for its overall growth and back up your argument there. And then finally is like make a decision of when each algorithm would be better than the other one. So ranges of values in certain cases. So maybe this one's better if you know your inputs are only going to be under 1,000. So who cares? Use the one that may be inefficient, but they're all so marginally different at time. Or you know you're going to be on the opposite side where you have lots and lots of data. So pick the one that's going to be more like run faster than when the data increases. So example, let's go and kind of talk about these quickly, which is roughly the most I'd ever get you guys to compare, is comparing big O's and everything else, or I gave you the growth functions, or you need to convert the code and get the growth functions. In this case, we have 3 algorithms, and we're just going to, we have been given their growth functions, and we want to compare which one could be better. So I'll switch over to where I can write down stuff then and start going through our steps to compare. So the first one is to figure out the big O of each one and then compare from there to see which one would be better. So on this first line right here, again, you look for the dominant term and then you drop any constants. Here we just have 3, we have 4 to the n squared n, and we already know that, again, n is less dominant than n squared, so this is our dominant term, and then we're dropping the constant. And so algorithm A has a big O of n squared. algorithm B, when we look at it, you have 2, you have 6 to the n, so this is the dominant term. We drop the rest of that and drop the constant, so we get order n. And then we get algorithm C, similar thing, that this is most dominant. Drop the constant, get rid of everything else, so we get order n. So at this first step, what we can realize, well, algorithm A, nah, that's not going to work because it's n squared. That's worse than comparing to these other two that are both n. So algorithm B and C are better than algorithm A. So we can just get rid of algorithm A, and that's not one of our choices because it's always going to run worse than any of algorithm B and C for the same problem. But now when we look at, oh, it's order n for both algorithm B and C, so we need to then differentiate, well, how do we dig deeper to compare the two of those? So we want to go instead, now that we've narrowed it down by looking at the growth functions, we want to say, okay, now we look at the big O. Now let's look at the growth functions, and we want to take each one of these and plug in a couple different values from this. So let's say I'll just arbitrarily bring in, like, say, we'll put in 1, we'll put in 10, we'll put in 20, and we'll put in 100. And we'll go through calculating each value. So this will be for algorithm B. Let me move all of this further down. So 1, 10, 20, 100. This will be algorithm B. This will be algorithm C. So the first one here is just plugging in, and this is n that we're dealing with. Blah. Going across here. So we have 6n plus 2. So that's 6 times by 1 plus 2 is we get 8 for algorithm B. And then for 1 here is 7 times by 1 is 7 plus 1 gives us 8 as well. So no difference to compare to right there. Next we go to 100. So these are the same. So at one value that's only 1 here. We get 6n plus 2. So if we plug in n being 10, that's 10 times by 6 is 60 plus 2, which gives us 62. And then for algorithm C, it's 7 times by 10 is 70 plus 1 is 71. And we can see the first indication that, okay, for 1 here, and we go up to 10, that there's starting to be a gap. We don't know if it's going to keep growing like that. That's why you have other samples that are arbitrarily picked here. But we got 62, but there is a gap of 9 time units between that. Next, we can go to 20. So 20 times by 6 is 120. Doing math in my head, which I'm always horrible with, so I will confirm. You can mock me by not being able to do math in my head too fast, but I like to confirm. So yes, it is 120. And then we do 7 times by 20 equals 140. So 140. Right here, make sure it looks more like a 0. So you get 120. We can see the gap widening between the two. And let's go to 100. Even easier to do this quick math then. That's 100 times by 6, so that's 602. And this is 100 times by 7 plus 1 is 701. And so we can see, if we look at each one of these numbers, similar, growing difference that's getting larger, then even larger one. And so C is taking, as the input's increasing, is that at lower ones it's marginable for the difference, but for larger values it's growing much larger to actually take. So I would not want to use C and say that probably B is better for us for our case that we're dealing with. So I would decide that B is backed by that, and I backed by my argument by explaining the big O's and referencing back to my samples that I actually took from there. And then we know that that could be the better one to go with. Okay. Switch back to the slides, even though we're basically done. A whirlwind hour of this and me talking faster in the video than you probably get in class. And we end from there. So that's our basics of time complexity. We'll reference back to these things. We'll have examples, but I just want to give that flavor of this timing. And we need this especially when we're getting to operations of data structures, because a lot of times then I could give you the different implementations of the same data structure and say, well, which one do we use? Then I'd expect you to start going and looking at, did I give you the big O's? Can you figure out the big O's of stuff? Can you compare the operations between two data structures? Say if it's the stack and we have two implementations of it and we're comparing the pop operations, and then we want to know, well, which one's better for pop? Which one's better for push? Which one's better for top? Those kinds of things. It's like which one's better overall to make our program run more efficiently. We can now start using the asymptotic complexity in our growth functions and the big O to have terminology to be able to compare this and visually make these actual overall arguments. Okay, From here, you should go on to the next lecture material and the next tutorials, and I hope that all of you are still doing really good as this semester kind of keeps chugging along and as the weeks go by faster and we keep hitting closer and closer to the end of the course, even though it feels like we've just started, but that never-ending, constantly moving forwards and learning and learning and learning. And you learning that you will always be awesome, and I will never think otherwise. And continue to have a great day no matter where you are right now and what time and what's going on.